Then let's continue on with the idea of redox reactions and balancing those reactions. Now, as I said in our introduction today, our primary focus is going to be using something called the the oxidation number method. The oxidation number method is my preferred way of balancing these equations because so long as we don't have to break them apart into half reactions, this will balance the equations far more quickly, far more easily than anything else will. And so to that end, they are way more useful. But they are a little bit more difficult in terms of you really have to have your oxidation numbers down. You have to know what you're doing there. Now, in the second half of today, we will talk about the half reaction method. You don't have access to the learning lab, so I'm going to take care of that myself. We'll take probably about half an hour or so at the end of today's lecture to talk about that. And the half reaction method does have some utility. Again, if you end up having to take Chem 2, when you do the electrochem unit, the half reaction method is how electrochemical reactions are presented. But like I said, for our purposes here in this course, we usually just have to balance reactions, and the oxidation number method is a good deal faster. So let's get into what the method looks like. From the methodology standpoint, what we're going to have is a skeleton reaction. Now, the skeleton reaction is going to be a net ionic equation, where we start with 1 mole of each reactant that's relevant and 1 mole of each product that's relevant. So we saw examples of that in the previous couple of problems, where we had copper metal and copper ion, zinc metal and zinc ion, and we didn't concern ourselves with what those spectator ions were. That's the skeleton reaction. Now, the second step in this is to do what we just did in that hydrazine example. And in the hydrazine example, the first thing we did was we assigned oxidation numbers to everything. And that's exactly what you're going to do in this case as well. The only difference is that in addition to doing the oxidation numbers, you're going to calculate the change in oxidation number for each element. And we kind of did that, but not nearly to the same degree. The thing that's different is we are going to calculate the total change in number for all atoms of the element. And that's going to be the important difference for us. So in the case of the previous example where we had the hydrazine and we were doing all of that, we only said, okay, the +4 here is turning into a 0. And so it had to, we had to take in 4 electrons. In the balancing part, we would say, okay, well, hold on a second. There are 2 of those nitrogens. Each one gains 4 electrons. So 2 times 4 would be 8 electrons in total that need to be gained. And then we would do the same kind of thing for the nitrogen here. I had 2 nitrogens that were each losing 2 electrons. And so the reason this 2 is out here is to balance that out and get the totals to work out correctly. So we'll hit that spot here, because the next step is, once we've figured out the total change in number, now we're going to use coefficients to balance out that change, because the most important thing in a redox reaction is that we have to have a balance of charge. And that means that every single electron that is lost by the thing that is oxidized needs to be absorbed by the thing that is reduced. And so there can't be any electrons left over in either direction. I can't have a reduction that requires 9 electrons if the oxidized species only gives up 5. I'm going to have to balance that out in some kind of way. And so coefficients are going to be the thing that ultimately does that. Now, in the process of doing that, every element that is not hydrogen or oxygen will also be balanced in the process. And then finally, the last 2 steps kind of run into each other. Step 4 is we're going to balance the total ionic charge on the reaction by either using hydrogen ions if the reaction is occurring in acid, or hydroxide ions if the reaction is occurring in base. That'll fix the charge issue, and then we'll use water at the very end to fix the hydrogen and oxygen issue. And normally speaking, that change, step 4 is probably the most difficult of the, because we have to get it right and we have to make sure that we calculate our charges correctly. Once we do that, though, the last step's usually pretty intuitive. And more often than not, we can base it on the hydrogens. So, you know, if I add 12 hydrogen ions to the product side, I'm going to need to add 6 waters to the reactant side to give me those 12 hydrogens back. It's usually something along those lines. It's pretty intuitive. And that's it. That's the entire process. It all fits on this one slide. But the best way to go about this is to do a number of examples, and that's where we're going to be today for the most part. So in example 6 here, I've got a nail. It's made out of solid iron. I put it into a solution of a soluble palladium 2 salt, and the nail starts to disappear as the iron enters the solution as iron 3+. What is the redox reaction here? Well, the first thing that we would do is we would set up that skeleton net ionic reaction. I've got iron in the solid phase reacting with palladium. And I know that it's palladium 2+. And I know that it turns into iron 3+. And it doesn't tell us, but we're pretty safe to assume, because palladium only has 2 well-known oxidation states, that the other state here is going to be solid palladium. So my first step is going to be to, now that I've got my skeleton reaction, that is going to be setting up my oxidation numbers. So I've got iron here. Iron is in an elemental state, so its number is 0. Palladium is monatomic ion, so its charge. Same with the iron. This palladium is in an elemental state, so it is a 0 state. I've now assigned all of the oxidation numbers. Now I need to go about assigning changes in oxidation number. I'm going from a 0 state to a 3 positive state. In the iron, 0 to positive 3 is an indication that I have lost 3 electrons. Palladium is going from a positive 2 state to a 0 state. So that means that it has gained 2 electrons. Now, in this case, since I have 1 of each of these, I don't have to do anything else with it. The total movement of electrons is the same as the change of oxidation numbers. The only thing that is left to do is I have to balance out the movement of these electrons. I have 3 electrons being lost by the iron, but only 2 electrons coming back to the palladium. So the way to handle this is using a lowest common multiple. Lowest common multiple between 3 and 2 is 6. So I'm going to multiply each one of these reactions by a number to get it to 6 electrons in total. So 3 times 2 will give me 6 electrons lost. 2 times 3 will give me 6 electrons gained. And these multipliers are going to become our coefficients in the equation. So the iron gets a 2 here and a 2 here. And the palladium gets a 3 here and a 3 there. And so from this standpoint, I've now balanced. My irons are balanced. I've got 2 on each side. My palladiums are balanced. I've got 3 on each side. And because of this calculation, I now know that I have an equal number of electrons leaving the iron as being taken in by the palladium. Now it's just a matter of determining total charge. To determine total charge, we do something very similar to what we did when we first started balancing equations. We split this sucker in half. The total charge on iron is 0. The total charge on palladium is positive 2. 0 plus positive 6 is positive 6. So the total charge on the reactant side is positive 6. On the product side, I have 2 iron 3 pluses, so 2 times positive 3. I have 3 palladium zeros. So now I have 6 plus 0, so positive 6 over here as well. Since the total charges are even, no further balancing is required. So we didn't even need to do the last couple of steps where we had to deal with hydrogen and oxygen. There is no hydrogen and oxygen in the equation currently. We have an evenness of charge, so we don't need to add anything. What this also means is that this particular reaction is equally likely to occur in acid, base, or neutral solution, which is an important thing to know. Now we will find this to happen more often in acid just as kind of a default, but it doesn't have to be. But the important thing to remember with the balancing of this equation is you had to balance both the charge and the atom. If I had gone back and just did this the way that we used to, no oxidation numbers, nothing of that sort, we would have probably looked at this and said, it's balanced already. I've got 1 iron on each side. I've got 1 palladium on each side. The problem with that line of thinking, obviously, is that we haven't accounted for the charge. And that's important because in a net ionic equation, charge hasn't been considered up until this point. So all of this stuff that we did is actually relevant because we needed to account for the fact that it wasn't just atoms rearranging here, it's the literal transmission of electrons from one element to the other. So iron is literally giving its electrons to the palladium to ion here. All right, any questions about this example?
No.
All right, then let's go and look at another example here. So in this example, we are given the oxidation of chloride by perchlorate ion. And we're asked to balance the equation in both acid and in base. Now, with the oxidation number method, this is actually pretty easy to do because the first few steps are identical, and it's only the last two steps that we have to change anything. So let's approach it from the standpoint of just generally speaking, let's start to balance this equation. And to that, I'm going to need to assign oxidation numbers. Oxidation number for chlorine in perchlorate is +7. The oxygen is -2. The oxidation number for chloride is -1. The oxidation number for chlorine in the chlorate ion is +5. Oxygen is still -2. And then chlorine here is going to have a 0 number. Now, one of the things that you can do that help a lot is oxidation and reduction usually kind of show up in terms of matched pairs. So if I want to figure out what happened to the chloride, the best course of action is to look at, okay, what happened in the chloride here versus here? This is what we would call a matched pair. The difference between them is only one oxygen or two oxygens or something like that. Whereas the chloride and the chlorine here, that's another matched pair. I'll actually change their color here to make it a little bit easier to see. They're another matched pair because neither of those species have oxygen. Now, one thing that we need to fix before we move anywhere near forward here is we need to fix the fact that my chloride here has only one chlorine, but its partner has two. And so before I do anything else, I'm actually going to fix that right now by putting a preliminary coefficient in there to show that the chlorides become chlorine and that there are two of them that have to react. I have to have two chlorides in order to make a chlorine molecule. If I skip this step, the rest of my math is going to come out as half done. And I'm going to end up with the wrong answer because it's half done. And I'm going to end up not being able to balance the atoms. So from this perspective, now again, looking at the concept here of matching pairs, I can see that in the pink pair here, we have two chlorines going from -1 to 0, which means that a total of 2 electrons are lost. Each chlorine in this scenario loses 1 electron. There are 2 chlorines in total, so 2 electrons are lost overall. And for the blue scenario, I can see that I go from +7 to +5, which means that 2 electrons have been gained. So since this is the case, what I can also see now is that my electrons gained and my electrons lost are equal to each other. So I don't have to do anything more with coefficients here. The only thing I'm going to do is rewrite this equation just so it's a little bit easier for me to see all of the charges that are involved. So I'm going to put this in here. I have the perchlorate ion reacting with 2 chloride ions to make chlorate and chlorine. So there's my reaction thus far. Now, the next thing to do, I need to evaluate total charge. Total charge, I have a -1 for the perchlorate plus 2 -1s for the chlorides. -1 plus -2 gives me -3 total. On the opposite side, I have a -1 ion for the chlorate and a 0 for the chlorine. That's a -1 total on the product side. Now the next step here is to fix the total charge. And how we fix the total charge depends completely on what we're doing. Are we in acid or are we in base? If we are in acid, we're going to add hydrogen ions. If we are in base, we're going to add hydroxide ions. So since we're doing acid, let's do acid first. And if we're doing acid, we're going to need to add H pluses. Adding positive ions means we're going to have to make one side more positive. So we're going to pick on the side that's more negative. To turn -3 into -1, I need to add 2 H plus ions. If I do that, my -3 becomes a -1, and now it matches. Now to counterbalance the adding of the H pluses, I'm going to have to add a number of waters to balance out the hydrogens, and it'll just take 1. 2 hydrogens come from 1 water, so 1 water molecule will make the difference. And so my balanced equation in acid is going to be the perchlorate ion plus 2 chlorides plus 2 hydrogen ions yields the chlorate ion, ClO3-, chlorine, Cl2, and water. And that's really all there is to that. And so this is the reaction if it occurs in acid. Now, what if we were in base instead? Well, everything up until this point here would be exactly the same. We would evaluate the total charges. The only difference would be how we handle the balancing of those charges. Since we are in base, we would add hydroxides. And so we would need to add hydroxides to the less negative side to make it more negative. And so if I add 2 hydroxide ions here, that would turn my -1 into a -3, which would make it equal the -3 over here. As before, I added 2 hydrogens over here, so I need to add a water molecule over here to balance out those hydrogens that were added. And then I rewrite. Perchlorate plus 2 chlorides plus water makes chlorate, chlorine, and 2 hydroxides. Again, this would be the balance if it was in base. So again, the beauty of this particular system is that it works, and up until the very last step, up until this spot right there, where we add the hydroxides or the hydrogens and the waters, up until there, it is exactly the same process either way. It's just getting to that spot. That's kind of the more difficult part. You really have to have your oxidation numbers down. You have to be able to set it up correctly. And so that's where you can really run into problems, and that's where a lot of people can end up struggling with this. Any questions here about example 7?
Not really.
All right, let's clear the deck then and do another example, and then we'll go ahead and take a break. All right, in this example, we have the iodate ion reacting with sulfur dioxide to make iodine and sulfate ion. And so we start exactly the same as we did in the previous problems. We need to assign oxidation numbers. Iodate in this is +5. Oxygen is -2. The sulfur is going to be +4. The oxygen is going to be -2. The iodine is going to be 0. The sulfur in sulfate is +6 and -2 in oxygen. And so setting up the matched pairs here is pretty easily. There's only 2 substances that contain iodine. There's only 2 substances that contain sulfur. So this one isn't as difficult to do. Let's just go ahead and box those in. We'll choose blue for the iodine. We'll choose pink for the sulfur. One other thing that we should look at and point to as far as the iodine is concerned, notice again that we have 2 iodines in my product, but only 1 here in the reactant. So before we do anything else, let's even that out so that we know and that we're working with the same numbers of each species. So now with that in mind, I can see that for the iodine, I'm going from 2 versions of +5 to 0, which means that a total of 10 electrons have been gained. Each iodine going from 5 to 0 means that it gained 5 electrons. The fact that there are 2 of them that underwent that, 5 times 2 gives me that 10. If I look at the sulfur, I can see that the sulfur is going from +4 to +6. There's only 1 sulfur in here, and so 2 electrons are being lost by the sulfur in this case. And so this presents for us a dilemma. Iodine requires 10 electrons to go. The sulfur is only capable of giving it 2. So what has to happen is that the sulfur reaction has to occur 5 times to give us those 10 electrons lost overall. And so that's going to come in the form of, we need to put a couple of 5s in here around the sulfur-containing atom substances to give us 5 sulfurs to react and lose the total of 10 electrons. So we've handled the first couple of steps. We have evaluated the oxidation numbers. We have evaluated the total number of electrons moving. We have added coefficients to make sure that all the electrons leaving are absorbed and vice versa. Now let's rewrite to be a little bit more clear. I have 2 iodates reacting with 5 sulfur dioxides to make iodine and 5 sulfates. The next step in the process is to divide the reaction in half and evaluate total charge. So I have 2 -1 charges for the iodates and 5 uncharged sulfur dioxides. So a total charge of -2 on the reactant side. On the product side, I have uncharged iodine and 5 -2 charged sulfate ions. So a -10 total charge. And now comes the part where we have to actually to change course. For acid, we add H+. For base, we add hydroxide. So for our acid reaction, we are going to add H+. So we need to add 8 H+ ions to turn that -10 into a -2 and get it to match up with this -2. Adding 8 H pluses means we're going to have to add 4 waters to balance out the hydrogen. And so our reaction in acid is going to look as follows. Two iodate plus 5 sulfur dioxide plus 4 water makes iodine and 5 sulfate and 8 hydrogen ions. If this was in base instead, all that really changes is this last step. Where we would be adding hydroxides instead of hydrogen ions. So we would add the hydroxides to the less negative side. So 8 hydroxide ions, which would give a total of -10 to the reactant side to match up the -10 on the product side. And then to counterbalance those hydrogens, I would have to add 4 waters. And so the reaction in base would be, again, practically identical, just one different component. 2 iodates and the 5 sulfur dioxides and the 8 hydroxides making iodine, 5 sulfate ions, and 4 waters. So like I said, the real trick, the hard part here is in those first couple of steps. Once you get to that part and you get through here, the last part's relatively simple, and it really doesn't matter which direction you go. It falls into a relatively predictable kind of pattern.